Let's now solve 3 exam questions about forces in equilibrium. The first of which is this one. This is from a spring 2014 question paper 42. It's question 3. You have the diagram, okay? I'm going to read through the text to see if there is any hidden information here that is not represented in the diagram. So A and B are fixed points on a vertical wall with A vertically above B. A particle P of mass 0.7 kilograms, well, you have the mass of the particle, is attached to A by a light inextensible string of length 3 meters. This light inextensible string is what you are always going to read about strings, meaning that the light means that the mass of the string doesn't matter. Inextensible means that this length is the length that you're going to deal with throughout the question. Is not extensible. So in a nutshell, you don't need to worry about the physical properties of the wire. Okay, P is also attached to B by a light inextensible string of length 2.5 meters. P is maintained in equilibrium at a distance of 2.4 meters from the wall by a horizontal force of magnitude 10 newtons acting on P. Both strings are taut, and the 10 Newton force acts on a plane APB, which is perpendicular to the wall. Find the tensions in the strings. So, with the exception of the mass, all the other information is represented in the diagram. These diagrams are never to scale, okay? So, you have to retrieve all the information from the text itself, all right? Cannot assume anything based on the diagram itself. All right, I made here a representation of the diagram. Let me zoom in. You need to find the tensions in the strings. You have 2 different strings. This means that you have 2 different tensions. All right? As I told in lesson, what is the method that you should always use to solve these types of questions about equilibrium? And about all questions in mechanics for that matter, in which you have to represent forces. The first thing is to choose appropriately the referential. And you choose the referential in a way that minimizes the effort of decomposing forces. All right? In this case, you have 3 forces. You have the tension T1, which I call T1. You can label the tensions as you wish. I call this one T1. You have the tension T2. You're going to see why I did this T2 much smaller than T1. And then you have the force, the 10 Newton force. I picked the referential, as you can see here in purple, so that this 10 Newton force must not need to be decomposed, because I have the information required to calculate these angles over here that are going to be linked to the decomposition of these 2 forces. You could actually use these angles to decompose the 10 Newton force, but this will give you an extra burden. Okay, so I put X as this horizontal axis and Y as this vertical axis, meaning that the 10 Newton force is going to be on top of the x-axis, meaning also that I will have to decompose T1 and T2. In all of these questions, the system is in equilibrium. This means that the sum of all forces needs to be 0. When you're dealing with the decomposition of forces, when you're dealing with the positioning the forces in a system of axes, in x and y, this means that the sum of the forces in each one of these axes also needs to be 0. The sum of all forces or components expressed in the x-axis needs to be 0. The sum of all forces or its components expressed in the y-axis also need to be 0. Okay? So that's the main concept that you have to follow throughout all these questions. I told you that you'll need to decompose T1 and T2, and for that you need the values of these angles. So I started by calculating how much this angle that I labeled alpha is, and how much this angle that I labeled beta is. And for that I use the fact that you have here rectangle triangles and you have the lengths of these sides. So for this rectangle triangle, this 3 meter would be the hypotenuse, this 2.4 would be the opposite, so opposite and hypotenuse, it's the sign that you have to look at. So alpha equals sine -1 of the opposite over the hypotenuse. So here is the angle, it's 53.1. I did the same thing for beta, okay? And I got the angle 73.7. So now that I have this out of the way, I can focus on the distribution of forces over here, okay? So on point P, what do I have? First of all, you need to know that this is in equilibrium. So this 10 Newton force, which is the only one that you have on the x-axis pointing in the positive direction, has to be compensated by the horizontal components of T1 and T2. In other words, 10 needs to be equal to T1x, which is the horizontal component of T1, plus T2x, which is the horizontal component of T2. It's very tiny over there. I hope you can see it over there. So that's for x. Same thing must happen for y. And for y, what do you have? You have the vertical component of T1. You have the vertical component of T2, and you have a force that I forgot to mention a little while ago, a very important one, which is the weight of the particle. That actually helped me decide to put the x and the y-axis the way I did, because this enables me to have the 10 Newton force and also the weight on top of one of the axes. No need to decompose these two, okay? So in terms of y, what do I have? Pointing up, I only have the vertical component of T1. I only have T1y. Pointing down, I have the weight plus the vertical component of T2. And this is the information that I needed to figure out the relationship in size and magnitude of T1 as compared to T2, because I know that the vertical component of T1 alone has to be enough to compensate for the weight and the vertical component of T2. So the vertical component of T2 must be much tinier than the vertical component of T1. All right? So T1y equals the weight, which I always represent, as you know, as Fg, force of gravity, plus T2y. In terms of mechanics, the question is over here. Everything else is just calculations and dealing with angles and trigonometry and stuff and calculations. The main concept is here. I say always this: a good diagram is half of the question answered. Okay, so if you are able to reproduce what is being described accurately in a diagram, and then if you are able to translate this diagram into math, which is this part over here, practically all the parts related to mechanics, related to understanding of the concepts, it's done. Everything else from this point onwards is just calculations. So let's do it, okay? T1x, what is T1x? This part over here, trigonometry. You have here a rectangle triangle. T1 is the hypotenuse. This one is the adjacent. But sorry, you must not look to this triangle. You must look at this one over here. Why? Because you calculated this angle alpha, which is the same as that over there. Okay? You could use this, but this would be 90 minus alpha. It will be an extra calculation that you don't need to worry about. So instead, just focus on this triangle. You can pick whichever, this one or this one. So if you pick this one, now the horizontal component, the size of this vector over here, is the same as that over there, right? And that, in relation to this rectangle triangle, is the opposite to this angle. So you want the opposite, you know the angle and you know the hypotenuse, so that's the sign that you use. Okay, so T1x is going to be T1 sine of the angle alpha. And the same argument goes for T2x. Again, you are using this tinier angle over here. This angle is the beta angle over there. So the T2x, the tiny one over there, is the same as that one, which is the opposite to the angle. So you also use the sine. So T2x is going to be T2 sine of beta. A similar argument can be used to calculate now the vertical components. In relation to this angle, T1y is going to be T1 cosine of the angle, and T2y is going to be T2 cosine of the angle beta. All right, so that's what I have here. Okay, we know the values of alpha and beta. We already calculated them. And you want to know T1 and T2. That's the question. Yes, you need to know T1 and T2. That's basically your last unknowns. Okay, so just substitute. I I use the bottom one to put everything in terms of T1. So T1 is going to be 7 plus T2 cosine of 73.7 divided by cosine of 53.1. I substituted that on top over here. Okay, don't forget that sine of an angle divided by cosine of the same angle is a tangent of that angle. All right, if you would just plug in the values in a calculator, you will still have the same result. Okay, so this eventually is going to lead to this value over here, which is now everything in terms of T2. You can solve it for T2, substitute T2 where you left the previous expression over here, and you get T1. Sorry, over here, and you get T1. All right? Okay, let's see how this method is used in every single question. So we are now moving on to a November 2004 paper, question 3. You have this diagram over here, and it says, each of 3 light strings has a particle attached to one of its ends. The other ends of the strings are tied together at a point A. The strings are in equilibrium, with 2 of them passing over a fixed, smooth horizontal pegs, and with the particles hanging freely. So these work as pulleys. The weights of the particles and the angles between the sloping parts of the strings and the vertical are as shown in the diagram. Find the values of W1 and W2. W1 is the weight of particle 1, W2 is the weight of particle 2. So, how many strings you have? You have this one, 1, you have this one over here, 2, and you have this one over here, 3. So you have 3 strings attached together with a knot, so you will have 3 tensions, okay? You have those angles. So let's go back to my own representation. It is over here. What information are you given? That this is in equilibrium. Okay, so if it is in equilibrium, we can focus on each particle individually. What's going on with this particle? There is the weight down, and there is another force that is keeping it in place, which is a tension 1, right? So the weight 1 equals a tension 1. That's what I have here only for particle 1. I label this particle 1, this particle as being 2, this particle as being 3, okay? On particle 2, what do you have? You have the weight of particle 2 equals to the tension that you have over there, which I call TA. All right? I called this one tension 2, just to be with the same name as they used in the question. They call this W2, so weight 2. So I call this one tension 2, this one tension 1, and this one tension A. Let me just say here that you can call whatever you want as long as you keep those labels the same throughout the question. Otherwise, eventually it will be a mess. Decide what you want to call to what, and then keep that from the beginning until the end of the question. And make a label such as this one so that the examiner knows what you are referring to. All right? That's very important. Okay, so here on this particle is the same thing, the weight equals the tension. So basically you have the same situation. If you think of each particle individually, the weight of each one is equal to its tension, right? That's how you're going to get the value of W1 and W2. You need to calculate the tension over here, and you need to calculate the tension over here. You need to calculate what I called T1 and T2. And in order for me to do that, I now have to think of the whole thing as a whole system. Where do all these things meet? They meet here at point A. So that's where I have to focus all the physics, all the statics related to this question. This is in equilibrium, so all the forces applied here, they have to cancel out. If you break this down into X and Y, all the forces that are decomposed in the x-axis and the y-axis have to equal to 0. That's the same thing every time you have questions regarding equilibrium. All right, so on point A, what do you have? Let's look at the forces that you have. You have the weight, you have the tension of A, okay? The tension of A on point A is down. I represent it here as a vector. Okay, All the forces here on point A that matter to this question are represented in blue. You also have these two in blue, but yeah, here on point A, the forces that matter are the ones represented in blue. So this tension A over here is applied on particle 2, all right? The one that you see here is the action-reaction counterpart, so is a force of equal size but opposite direction that is now pointing down. This one is applied in A, all right? So you have this force down in A. You have this tension over here and that tension over there. Since this is a string, the same string, this tension must be the same as that one in magnitude. And this one must be the same as that one in magnitude. This is how you're going to get T1 and T2, which will be the same as the weight 1 and weight 2 that the question is asking for, right? Okay, and these are the only three forces that you have. You have the tension A, you have the tension 1, and you have the tension 2. I decided to use this referential XY. This means that I will need to decompose T1 and T2. TA is already on top of the y-axis, no need to decompose that. And if I use the angles that the question is giving me, so I will use this triangle to get the horizontal and vertical component of T1, and I'll use this triangle to get the same for T2. Okay, so after decomposing, this is T1x, this is T1y, this is T2x, this is T2y. How do I know that this is smaller than that? Same argument that I used in the previous question. I know that the horizontal component of this force needs to be the same as the horizontal component of that force. T1x must be equal to T2x. They are, after all, point A and everything else is, after all, in equilibrium, right? If that's the case, because this angle is bigger, then the vertical component of this force is going to be smaller. And this plus that put together must be equal to TA. Okay? Once again, all the mechanics, once you have this done and once you translate it into math, and here you have it on point A in x, T2x equals T1x, and T1y plus T2y equals TA. All the mechanics is done. Everything else from this point onwards is just math. And trigonometry, trigonometry is part of math. All right? So again, what is T2x? T2x is this part over here, which is the opposite side to this triangle over there. So you use the sine is T2 sine of 60. The same reason for T1x is T1 sine of 40 now. And for the y components, you are using the cosine. T1y is going to be T1 cosine of 40, and T2y is going to be T2 cosine of 60. And you know that this must be equal to 5, all right, which is the weight of particle 2. Okay, so I solved this in terms of T2. I substituted there here underneath, all right. I just then solved this for T1. I got a value. I substituted on top where I left it, and I have a value also for T2. And final answer, I know from the very beginning that T1 equals the weight 1 and T2 equals the weight 2. So here you have them. Okay, are you getting this? Let's see another one. I think this one, okay, this one uses a ramp. It's from a winter 2014 paper 41, question 2. You have a ramp and small blocks A and B are held at rest on a smooth plane. Smooth plane, what does smooth mean? Smooth is the best thing that can happen to you. Smooth means you don't have to worry about friction. Rest on a smooth plane inclined at 30 degrees to the horizontal. Each is held in equilibrium by a force of magnitude 18 newtons. The difference is that the force A acts upwards, parallel to a line of greatest slope of the plane, and the force B acts horizontally in the vertical plane containing a line of greatest slope. Okay? This is horizontal, this is up the slope. The magnitude is the same. Find the weights of A and the weight of B. Okay. Let's look at each one of these individually. Here at green, I have the same thing that the question was telling you. And here I divided this in two situations, A and B. What is happening over here? I've never liked the forces applied to objects represented the way they are over here. I always try, although this is not technically correct, the point of application of a force is not always in the center of the object. In mechanics, you can always treat objects as point masses, all right? I like to keep them as objects with dimensions for you to have a perception that this is something that comes from the real world, but you could nonetheless represent the box as a single point. And if it was a point, all forces were applied in the same place, okay? So I mix the two. I keep this as a box, all right, as an object, a random object, but I apply all forces on the same spot, because this enables me to break down the forces on its components much easier. So what does this mean? This means that this 18 Newton force is applied at the center of the block and points up. Here it is. See? It's the same. Okay? The weight is applied down. And the third force that you have is the normal contact force, which is always perpendicular to the plane. So it points up. In this particular case, the normal contact force needs to be equal to the vertical component of the weight. Before that, which force am I going to decompose? It's going to be the weight. Why? Because this happens in most situations. It won't be on this one, by the way, but it is still on example A. The horizontal component of the x-axis will always be along the slope, meaning that the vertical axis is going to be perpendicular to it. In most situations, the force that you'll need to decompose is the weight. Okay? Why? Because in this case, the weight is the only force that you'll need to decompose. If you will put it like this, then you'll have to decompose the 18 Newton force and the normal contact force. More work. The result should be the same, but it will be more work. In this case, it's just the weight that you'll need to decompose. And you should know by heart, the inclination of the ramp is always this angle over there. Okay? If this is 30, that is 30. So you have all the information required. You focus on this rectangle triangle. The vertical component of the weight is going to be the adjacent to the angle. So you use cosine for this one. The horizontal component of the weight is going to be this side over here, the opposite. So you use the sine. Okay? That's all that you need to know to solve the question. So let's translate this into math. Again, this component is the same as the normal contact force, and the horizontal component of the weight must be equal to the 18 Newton force for this to be in equilibrium, right? So on x, you have 18 equals fgx. On y, you have the normal contact force equals fgy. What is fgx? Fgx is, as I told you, Fg sine of 30. You know what? You don't know the weight. Yes, you can calculate the weight. So the weight is, that's the only thing that you wanted. Yes. Okay, it's simpler than that. The weight is then 36 Newton. 18 divided by sine of 30, that's 36 Newtons. All right? What if the 18 Newton force is applied like this? In that case, it would be simpler to represent the referential the way I did right now, because the x-axis would be on top of the 18 Newton force, the y-axis would be on top of the weight, meaning that you would only have the normal contact force to break down. Okay? And where is this 30-degree angle now in this representation? Well, continue this line up, right? This would be the y-axis that you have right now, along the weight. This 30-degree angle will be equal to that, okay? This is what you have over here. The 30-degree angle is over there, all right? The same situation is valid. All the components in the x and the y-axis must be equal. So now that you are decomposing the normal contact force, it is the horizontal component of the normal contact force that is equal to 18, and the vertical component of the normal contact force that equals the weight. That's what I have over here. And that's how I'll get the weight. All right. So 18 equals n sine of 30, the opposite side, right? Sine of 30. Okay, so I can get directly the normal contact force is 36 newtons. I plug it over there and I get the Fg. Fg is 36 times cosine of 30, so it's 31.2. Okay, that would be the answer for the last question. Practice with more of these questions. You'll see that the mechanism is always the same. Looking at the diagram, choosing the right referential for each one, decomposing the forces that need to be decomposed, sum all the forces in x and equal to 0, or like I do, equal the forces pointing to one side to the forces pointing to the other side. Do the same thing for the y-axis. Mechanics is done, then it's just mathematics and solving simultaneous equations to figure out whatever you are being asked.